Good morning. So today we will start a new topic from this chapter, which will be the last topic called entropy. Have you heard of entropy before? Have you ever learned anything about entropy? What is meant by entropy? I hope this will be a new topic to you. To get into entropy, let me consider a situation. Suppose you have something, maybe 1 kilogram of water having 100 degrees Celsius. And you have another vessel containing 1 kilogram of water at 10 degrees Celsius. So you have very hot body here and very cold body here. Now, if you place a working substance like a gas in between, and if you connect this engine, there is a possibility that you can take heat from the hot body, convert a part into work, and give the remaining to this cold body. Suppose you are taking an amount of heat Q1, you can convert it to work and you can give back the remaining amount Q2 to the cold body. So this process can continue and you can do some work from the energy which is there in these two systems. That this is 1 kilogram of water at 100 degrees Celsius and 1 kilogram of water at 10 degrees Celsius. And we call it a heat engine. Heat engine means a device that can convert heat energy to work. This is possible, right? Now, suppose I mix these two waters, so I will get, instead of 1 kilogram here and 1 kilogram here, I will get 2 kilogram of water, and at a temperature which is the average of these two, 100 plus 10 divided by 2, which will be about 55 degrees Celsius. Now, can we draw the energy from this body and convert it to work? Both of them are of the same mass, they have the same amount of energy. Now, in this situation, we can convert it to work. Now, in this situation, can we convert this to work? The energy possessed by the system into work? Is it possible? No. So the same system, if it is separated and at higher different temperature, we can draw work. We can convert the energy of the system into work. Now, if the same amount of substance at the same temperatures when mixed, what happens? We cannot convert this energy into work, the energy of this system into work. So there is something that is changed from this to this. That is called entropy. So when you are asked what is meant by entropy, one way to explain or one way to define entropy is that it is the inability or the disability. It's the disability to convert the energy of a system to work. So what is meant by entropy? It's the disability to convert the energy of a system to work. So the disability to convert the energy of a system to work is called entropy. So there is something about a system that enables the energy of the system to get converted to work, and if something changes from the system, it's not possible to convert that energy into work. And that something is called entropy. And you cannot find the actual value of entropy of a system, or the absolute value of entropy of a system, what you can measure is the change in entropy. Change in entropy. Okay. Entropy is represented by a letter S. Capital S represents entropy. And change in entropy represented by ds is equal to dq by T, where dq is the amount of energy given to or rejected by the system. So dq is the amount of heat energy entering a system or rejected by a system, and T is the absolute temperature, which means temperature in Kelvin. So you cannot find the absolute value of entropy of a system. What you can do is whenever heat energy enters a system or leaves a system, you can calculate the change in entropy of a system. Now we learned different kinds of processes, right? We learned isothermal process. In isothermal process, what is remaining constant? In isothermal process,
Temperature.
temperature is remaining constant. In isobaric process,
Pressure.
pressure, and in isochoric process, volume. But in adiabatic process, suppose it is adiabatic process. In adiabatic process, we didn't learn that some of the thermodynamic quantity remains constant. Instead, we learned that it's a process in which no heat energy enters the system or leaves the system, which means dq is equal to 0. Or you can say if dq is equal to 0, ds is equal to 0, which means the change in entropy is 0. So entropy is a constant. So you can also define entropy as that remains constant during an adiabatic process. So now we can complete that equation, like for isochoric, volume remains constant, isobaric, pressure remains constant, isothermal, temperature remains constant, and in adiabatic process, what remains constant? Entropy remains constant. So what is entropy? It is the disability to convert the energy of a system to work. Now, when you just define, it doesn't make a clear sense. So only if you consider a system which when is in a separated state, we can draw work from it. We can convert the energy of the system to work. And in the same system, if it is existing in a different state, what happens? You cannot convert the energy of the system to work. So there is something that changed between the system, and that is called entropy. So the entropy of a system as such doesn't have a valid meaning. We can only think about change in entropy. And change in entropy is measured as the change in the heat energy. That is the amount of heat energy absorbed by a system. In that case, it will be positive. And the amount of heat energy rejected by a system, that case dq will be negative, divided by the absolute temperature. And since ds will be 0 when dq is 0, S remains a constant, or entropy remains a constant in an adiabatic process. So did you get some idea about what is meant by entropy? Did you get some idea about what is meant by entropy?
Yes.
Okay. Now, when a body loses its heat energy or when it gains its heat energy, its temperature changes. We know that, right? Now, let us find an expression for the change in entropy with temperature. So, let us find an expression for the change in entropy when the temperature of the system changes. So, change in entropy and change in temperature. So when temperature of a changes from T1 to T2, let us see what is the expression to write the change in entropy, change in temperature. Note that the temperature capital T should always be in Kelvin. Okay. Now let us take the case of change in temperature. I told you that the change in temperature is represented the change in entropy. ds is equal to dq by dt, dq by t. dq is the change in heat or the heat energy given to the system or taken away from the system, and T is the temperature. Now, we have learned for a liquid the specific heat capacity represented by small s. This is small s, entropy is capital S or big S. The specific heat capacity of a liquid is equal to the amount of heat energy required to raise the temperature of 1 kilogram mass of a substance through 1 Kelvin temperature. So you can write S is equal to dQ by M into dt. dt is the change in temperature. So the specific heat capacity S is equal to dQ by M dt. So S is the specific heat. Now, from this expression, I can write dQ as equal to Sm into dt, right? I can write dQ is equal to Sm into dt. So let me express here ds is equal to Sm dt divided by t. Now, since we are trying to find an expression for change in entropy with change in temperature, suppose the system goes from temperature T1 to T2. So as the temperature goes from T1 to T2, as temperature goes from T1 to T2, the total change in entropy, delta S, is equal to, we have to integrate this. ds is a small change in temperature, change in entropy with a small change in temperature. So the total change when temperature goes from T1 to T2 will be integral from T1 to T2 Sm dt by T. Now here S is the specific heat capacity, which will be a constant, and if the mass of the system is not changing, M will be a constant. You can take both of them out of the integral. And what remains is integral 1 by t dt, right? dt by t means 1 by t dt. What is integral 1 by t dt? What is integral 1 by x dx? Natural log of x. So integral 1 by t dt will be log t. So instead of this, I am going to write log t. And log t, we have the limits from t1 to t2. So log t between the limits t1 to t2. So I will get it as delta S, the change in entropy, is equal to Sm. First, let me apply the upper limit, which is T2. So when I apply the upper limit T2, we'll get log T2 minus log T1. Or I can write it as Sm log A minus log B is log A by B. So log T1 by T2. So this is the change in entropy of a system when something goes from it's from T2 by T1. So change in entropy when the temperature of a system goes from T1 to T2 is equal to Sm log T2 by T1. Okay. Now here, let me consider one thing. Suppose a body is going from higher temperature to lower temperature. Higher temperature to lower temperature. Suppose the body is going from higher temperature to lower temperature. For example, a body cools down from 100 degrees Celsius to 0 degrees Celsius or 10 degrees Celsius. Higher to lower. So this T1 is smaller, right? Is bigger, right? So delta S will be a negative quantity, which means what? The entropy decreases. Entropy change is negative means the entropy decreases. So in this case, when a body goes from higher temperature to lower temperature, what happens? The entropy decreases. That's in the case of a liquid. Is that clear to you? Is this clear to you?
Yeah, teacher.
Okay, so that is how we can derive the expression for change in entropy with temperature. So this is an expression for change in entropy with temperature, but I would also like to discuss more about entropy to get an idea about entropy. Let us see some of the change in entropies in a reversible process and a irreversible process. Now, do you remember what is meant by a reversible process? What is a reversible process? What is meant by reversible process? You forgot what is meant by reversible process?
The reaction can be reversed.
Yeah, and you can get back the original thing. And the body will go through the same process as it went. Now, we were discussing about Carnot cycle. Remember, we discussed Carnot cycle. So this is a pressure, volume, gas. Is Carnot cycle a reversible process? My question is Carnot cycle a reversible process? Yes or no?
Yes.
It is a reversible process. Why? In a heat engine, Carnot cycle occurs in one way, and in refrigerator, the same Carnot cycle is reversed. So Carnot cycle is an example for a reversible process. So we are trying to analyze the change in entropy in a reversible process, and for a reversible process, we are taking the example of a Carnot cycle. So in a Carnot cycle, suppose a system is at stage A. At stage A, it goes through isothermal expansion and reach state B. Then it will go through a steeper adiabatic expansion and reach state C. And from C, it will go back first by a isothermal compression and then by a adiabatic compression. So this is D, this is DA. So AB is a, what is AB? AB is a isothermal expansion. Isothermal expansion. Suppose this occurs at a temperature T1. So during an isothermal expansion, what is the change in entropy? Change in entropy, let us represent it as dQ. So D is change in entropy is delta S. And in the first process, as it go from A to B, I'm going to express delta S1. So in the first process, this is the first process, isothermal expansion, delta S1. So in an isothermal expansion, what happens? The heat energy is absorbed by the system or emitted by the system? The heat energy is absorbed by the system. For example, in a heat engine, you have a hot reservoir at temperature T1 and a cold reservoir at temperature T2. Hot reservoir is the source of heat and cold one is called the sink where we deposit the extra amount of heat and you have a working substance. So a temperature or an amount of heat energy Q1 is taken from the hot source, a work is done, and the remaining heat energy Q2 is given to the sink. So this is what's happening in a heat engine, right? And the system goes through the Carnot cycle. So the first step, when it go from A to B, there is an isothermal expansion. So what is the change in entropy? Change in entropy is equal to, when you look at the system, it's receiving some amount of heat. What amount of heat? Q1. And it goes to the temperature of the source, T1. So I can write here delta S1 is equal to the amount of heat received Q1 divided by the temperature T1. So the change in entropy delta S1 is equal to Q1 by T1. The first process, that is isothermal expansion. Now the second process, as it goes from B to C, so as it goes from B to C, what is the kind of process? B to C. This is isothermal expansion. Next one is?
Adiabatic.
Yeah, adiabatic expansion. So what will be the amount of, what will be the change in entropy? It's an adiabatic process. So what is the change in entropy? Zero. We discussed earlier when we discussed what is change in entropy. It's that remains constant. What is entropy? That remains constant during an adiabatic process. So adiabatic expansion, the change in entropy is zero. Delta S2 is equal to zero. During an adiabatic expansion, no heat energy is absorbed or rejected by the system. So this is equal to zero. Now let us consider CD. What is CD? What is that process?
Isothermal compression.
Thermal
Compression.
compression. So isothermal compression. What is delta S3? So delta S3 means the amount of heat. Now this amount of heat is rejected, given out, right? So the change in heat energy will be minus Q2. Why minus Q2? Because heat energy is given out of the system. So I can write delta S3 is equal to minus Q2 divided by T2 because it occurs when at a temperature T2. So during isothermal compression, delta S3 is equal to minus Q2 by T2. Now the last process, dA. What is dA? Isothermal
Adiabatic compression.
adiabatic compression. Adiabatic compression. And in adiabatic compression, what will be delta S?
Zero.
Zero, because it is an adiabatic process. So we saw that in a Carnot cycle, this is the total changing entropy. So what will be the total change? Delta S1 plus delta S2 plus delta S3 plus delta S4. So let me express the total change during a Carnot cycle. The total change in entropy delta S during a Carnot cycle is equal to delta S1 plus delta S2 plus delta S3 plus delta S4. That is equal to Q1 by T1 plus 0. I need not write that. Minus Q2 by T2 plus 0. I need not write. So delta S is equal to Q1 by T1 minus Q2 by T2. But we know that the amount of heat energy absorbed Q1 will be proportional to T1. And the amount of heat energy rejected will be proportional to the temperature of the sink T2. So we know that Q1 by Q2 is equal to T1 by T2. Or when I rearrange, I can write Q1 by T1 comes down. T1 is equal to Q2 by T2. So From these two expressions, Q1 by T1 is equal to Q2 by T2. So Q1 by T1 minus Q2 by T2 is equal to what? They are equal. So if you subtract them, what will be the result? 0. See, the change in entropy for a reversible process is 0. So when a system goes through a Carnot cycle, what is the change in entropy? 0. There is no change in entropy when the system goes through a Carnot cycle. So for every reversible process, we are just generalizing the case. For every reversible process, the change in entropy will be 0. So what is the change in entropy for the adiabatic process? 0. What is the change in entropy for a reversible process? 0. So in all reversible process, the entropy will remain unchanged. The entropy will be equal to 0. So this is the point I would like to focus, that in a change, in a reversible process, the entropy change will be 0. And you also have to know what will be the change in entropy each of the process in a Carnot cycle. Is this clear to you? Is this clear to you?
Yes.
Yeah,
Okay.
teacher.
Now that is the change in entropy in a reversible process. Now let us see what will be the change in entropy in a irreversible process. In a irreversible process. Irreversible process. When we discussed irreversible process, we told that irreversible processes are spontaneous process or natural process. So all irreversible processes are spontaneous process. Spontaneous process means we need not do anything for that to happen. It will occur naturally. So let me take an example of such a case. Suppose I have here a substance which is at very high temperature, say 100 degrees Celsius or higher, and let me note it as T1. I have a body having temperature T1 and which is very high, and I have another body having temperature T2. T1 is very much greater than T2. Suppose I have water at 100 degrees Celsius, okay, and I have ice at 0 degrees Celsius. Now, when I connect between them, what will happen? When I connect between them, when I keep them in contact, I have a glass of water which is at very high temperature, and I have a piece of ice which is very cold. And if I keep it close to that, on a table, I keep the ice very close, touching with the glass of water, what will happen? What will happen when I connect between these two? When I connect between these two, the amount of heat will travel from one body to another. The ice will slowly absorb heat from the hot water and melt, right? So there is a flow of heat from one body to another. Suppose dQ is the amount of heat flowing from this hot body to a cold body. So what is the change in entropy? What is the change in entropy? As the temperature changes, what happens? The entropy changes, right? So when we look at this process, we know that for this system, T1, the change in entropy delta S is equal to, it is losing temperature. So for the first system, it's losing, so minus dQ by T1. And for this system, when I take the change in entropy, delta S2 is equal to, it's receiving the same amount of heat. So dQ divided by T2. So what is the
Your
top?
time finished.
Yes. Yeah, the time finished, right? Let me just complete this and I'll stop because I started late. Let me just stop this, or we'll do one thing, we will finish this later because I want to discuss a little bit more about change in entropy. So we'll continue that tomorrow, inshallah.